Okay, in this lecture we're going to continue on. In the last lecture we converted the transaction variable, which was a struct of listTxn type, to an array of structures, and we pulled out the print statements and so on and so forth. I think we added a print statement at the end, but I've taken that out again. And now this time we're going to write a function that we can call that will list all of the transactions that we've stored in the array. Whoops. Okay, so you'll recall in the last video I said, I had 1,000 transactions, but how do I know if that's enough? And then I put in, you didn't see this, but I put in a notion. I want to ensure that I have enough slots for 2 years worth of transactions. So what's one way I can look at that? Well, if I count this, I believe we have 213 transactions. Okay, and we do. But what are they? I mean, what time period does that represent? So you can see by looking at the dates, I have February 19th going down to February 1st. So that's not even a full month in February. Then I have January complete, and there's December complete. And so I only have a partial month for February, so I'm not quite sure I can rely on just averaging these over 3 months. But we'll just, for grins, we'll just pretend that 213 records over 3 months is the average. So I just simply need to divide 213 by 3. And that's 71. So because I have a partial month, I'll go ahead and say I average 100 transactions per month, just to be safe. So that being the case, I want to calculate how big to make my array of structures to make sure I have enough for 2 years. So if I say 100 is the average transactions per month times 12 months in the year times 2 years, that's my number. But we really don't like to put magic numbers in places. We'd have to write all kinds of comments there. So what I'm going to do is I'm going to define what 100 is and what 12 is up here. So I'll just do it like this. I'll say pound define months in year is 12, and then pound define average transactions per month is 100. Okay, and this is a way that we self-document the code. There's other ways to do this, but this is the way I'm going to do it for now. So I'll say in here, average transactions per month. Did I spell that out? I don't know. I'll figure it out. Times months in year. And this really helps people that come along and maintain your code, or that have to just read it to understand it for documentation purposes, anything like that. Okay, so that worked, and I'll run the code even though we won't see anything, but we're now allocating more space in the compiled program a.out because it's got to make room for all of that storage inside the program. Okay, so now that we have the pound define on 9 and 10, and now we have some rationale for how many structures I need to allocate. So that's basically 100 times 12 is 1,200 times 2 is 2,400. So I have enough room for 2,400 transactions. And since I'm only going to ever use 18 months of transactions, because in Wells Fargo, that's all they let me go back, then that should be a very comfortable amount of space to allow me to store everything without fear that I'm going to crash the program. It's not very sophisticated, but that's the way we do it sometimes. Okay, so now I want to create a function to list transactions so that I can show you that we've got all 213 of these transactions in memory in this structure. Okay, so I just added list transactions because that's what I want to do. Okay, but now we get the implicit declaration of this function, which means that it's not described in a header file, and it's not something that we have described to our own program, to the compiler. And so I'm going to go ahead and put in function prototypes. And I'll say this is a function that returns void. It's called list transactions, and it takes no parameters. Okay, now when I compile it, I've shown you this in a previous lecture. We got through the compile phase, but we blew up at the linker phase. The reason we got through the compile phase is we told the compiler, trust me, you're going to see list transactions, and I'm telling you, you're going to be able to forget about it. The linker will take care of finding the code. Well, after the compiler finished off, and it knew about line 111, because we told the compiler about it on line 21. So the compiler's not worried about it. It goes ahead and it compiles, fully trusting that the linker's going to find the body of code we need for list transactions. But we've never defined it, not in any one of the include files or in this program here. So now I'll go ahead and I'll define the function. I'll say void list transactions, and I'll give it a body. And now I have to think about, well, how do I list the transactions? I know I need access to the array. Which array? Well, the array that we defined on line 49. Transaction is an array of structs with the tag listTxns. So then that's what I want to do, is I want to put in here struct listTxns. Okay, and I'll call it we'll call it record buffer. We'll give it a different name. And I'm going to put a comma in here. And I'm going to put a pointer symbol here, and I'll tell you why in a minute. Okay, and then the next thing I need to know, if I pass reference or pointer to what we're calling the record buffer, but which is really the transaction array up here, we also need to tell it how many records there are in that transaction. Because one, we know, and two, an array in C and C++ is just trickery. It's not really a data type. It's just a way to name a whole bunch of contiguous memory of the same type with a single variable name. And so we have to tell it how many record numbers we've got. And so I'll say int record, what do I want to call it? I'll say transaction count. How's that? Transaction count. Okay, so now with these two pieces of information, we will have enough information to create a loop so we can loop through and print everything out. Okay, so if I'm going to give a pointer to a struct listTxns, then basically I just need to name the array. Because in C and C++, the standard array is handled by the compiler and by everything else as a pointer to the first element in transaction. The first element in transaction, meaning at txn0, is a structure of this type. And so basically I'm named txn, it sends a pointer to the variable so it doesn't copy this massive array in memory, which would take a lot of time. We're just telling the function, hey, here is where you can go in memory to find the beginning of txn. And I just give it an alias like recbuff. If you have a nickname, that's what this alias is. But it's really pointing to txn. Okay, and then for transaction count, we know we're keeping track of that. We'll send in recno and see if that works. Another option would be to pass in line num, but we'll see if this works or not. And we'll figure out are we starting at 0? Are we starting at 1? Is everything coming out fine? Okay, so before I put any body in here, I'll just put a null statement, and then we'll try and compile and see if things are working. Well, it seemed to like that, but we know that our prototype does not match what we just defined. And so the easy button for doing a prototype is to yank the declaration line, or the definition line, I should say, and then paste it in under prototypes, and then terminate it with a 0. So I'll do that, and then I'll go up here and get rid of that. Okay, let's see if we can compile it. Good. All right, so now that it compiles, let's actually put the body in. And the body is going to look something like this. We'll say 4, well, let me give it a tab here. 4, and I'm going to use int I equals 0. I is only known inside of list transactions. If there's another I up above on line 93, it has nothing to do with the I we just defined inside the for loop, inside of list transactions. That's known as scoping. Okay, and we'll say I is less than or equal to txn count. And then I'm going to want to bump I each time through the loop and use the comma operator, so I can also bump txn, recbuff, which is the pointer to the first structure in txn. So each time we increment recbuff, it's going to move the pointer to the next structure. So first time through, it'll be recbuff sub 0, then it'll be recbuff sub 1, or the equivalent of it, because we're using pointer notation. Okay, now for the business. We'll say, let's printf, and we'll do the date just like we did before. And only now we're going to say recbuff and use the special arrow, which is how you access a member when you have a pointer to a structure. We use the dot if we pass the structure, do a copy. But if we're passing a pointer to the structure, then we use the arrow. And I'll say date, and we'll see if this works. And that seemed to work, and it looks just like before. And now we'll finish up by adding some interesting stuff, such as, I'll say recno, or just record, %d, we'll say recno, txn count. So now we get our little thing here, but notice that's not working right, because when we pass recno in, it's 212 every single time. That's how we know how many records we actually processed. And so that was a mistake of mine, but it was a happy mistake because it allowed me to show you what txn count was. So I'm going to say I, because I cycles through from 0. Okay, so now it cycles through, and you can see we have 213 records. 213 because we start counting at 0. So for human consumption, for your users, you could simply say that record is I plus 1. And then if you wanted to show, hey, listTxn sub %d now we got pointers. I'll do it like this. I'll convert it so you can see if you were accessing it using subscripts rather than pointers, then this will show it to us. I'll say equals, and then I'll add I. So in this case, record count is the +1. The offset or subscript into the array buffer is I, but then we're actually calling it out because we passed a pointer in. But these are all getting us to the equivalent data. Okay, so you can see that record 213 is accessed by going to transaction 212.date, but then we actually pulled it out using the arrow notation because we're using a pointer. So you can see 3 different ways to get there. Okay, so then if we wanted to beef this up, we could dump this and we could say, okay, so we got the date. Now let's print the amount. Long float because it's a double. And let's see, in the original file, I think we got the cleared flag next. I don't want to print the cleared flag because I don't care about it. And I will say, let's print the check number. So that'll look like this. We'll say rec buff arrow and amount, and then rec buff arrow and check no. And then lastly, we'll put the description in. %s. And this will be rec buff arrow description. Let's see if this works or if I made a mistake here. Oh, date I is not going to fly. So I was trying to do insert. So get rid of that. It didn't like I. And that's because I forgot to put in, I forgot to take it out because I deleted that conversion character. Let's try this now. There we go. Okay, and so now we've chopped this file up, we've stuffed it into an array of structures, and we're now able to pull the fields back out at will, which means that we can now write other functions to do math and do, min, mean, max, debits, credits, you name it, we can do it. All right, so that brings us all the way through the end of this series of lectures, which takes us all the way from the beginning of class to something useful to give you a foundation to have a starting point into processing data from comma separated value files.